In this lecture, we're going to discuss random variables and probability distributions. We will focus on continuous distributions. In terms of the agenda, we will discuss what a random variable is and what a probability distribution is. We will then discuss the cumulative distribution function. Then we will focus on the normal distribution.
When we assign probabilities to each outcome, we are setting up the probability distribution. The probability distribution of a random variable says how the total probability is distributed among the various possible values of that random variable. You should note here that the probability for all of the outcomes in the sample space is 1. There are two main types of random variables in probability distributions. These are continuous and discrete. A continuous distribution is one where the possible outcomes consist of an entire interval on the number line. Some examples are the normal and exponential distributions. A discrete distribution is one where the possible outcomes either constitute a finite set or an infinite set with some natural sequencing. Some examples of these are binomial and Poisson.
There are two main types of random variables in probability distributions. These are continuous and discrete. A continuous distribution is one where the possible outcomes consist of an entire interval on a number line. Some examples are the normal and exponential distributions. A discrete distribution is one where the possible outcomes either constitute a finite set or an infinite set with some natural sequencing. Some examples of these are binomial and Poisson.
A random variable is considered continuous if for some a less than b, any number x between a and b is possible. If the measurement scale of x can be subdivided to any extent desired, then the variable is continuous. Some examples of this are given on the slide. Dealing with continuous distributions is somewhat different than what we saw with the discrete distribution. Note that for a continuous distribution, the probability that the random variable can take on some value exactly is 0. This occurs because we are dealing with area under the curve in this case. Also, for continuous distributions, we will use the probability density function, or PDF. This is different than a PMF, since a PMF can give us probabilities for exact values. We view this as a continuous version of a histogram. To find probabilities instead of summation, as we did for a discrete distribution, we will use integration. So for example, if we wish to find the probability that a random variable x is between a and b, we will integrate the PDF with respect to a and b. One other thing to note here is that greater than or equal to have the same meaning when dealing with continuous distribution. This should not surprise you since the probability that x is equal to little x is 0. Just as in the discrete case, the CDF is used to get the probabilities in the continuous case. CDF is the integral from negative infinity to x of the PDF. Now if a distribution has some lower bound, then it is the integral from the lower bound to x. Here is an example of how we find those probabilities. Notice that finding a less than or equal to is just using the CDF as is. If we want greater than, we need to use 1 minus the CDF. These are similar to the discrete case, although remember that for the discrete case we have some probability at an exact value. To get probability between two numbers, we will subtract the CDFs from largest to smallest. Also notice that if you are asked for the area under the curve outside these two values, we can just find the inside probability and subtract it from 1. This will come in handy when you're trying to find the percent defective based on some specification, or the probability of creating a defect. Now let's talk about some continuous distributions. First we will talk about the normal distribution. Let's motivate the normal distribution with an example. You are in charge of a 4-step process. With each step, the amount of material removed can be modeled by target plus variation. Now let's assume that the variation is set up like the roll of 1 or 2 dice. This implies that the entire process is like the summation of values on the rolls of 6 dice. Let's look at these distributions. If x sub n is a random variable representing the sum of rolling n dice, then on the slide there are the distributions for x1, x2, and x6. Notice that for x1 we have what we call a uniform distribution. Each of the 6 outcomes have equal probability. Now, as we add more dice, we get a distribution that is becoming more and more symmetric. By the time we get to the sum of all 6 dice, we see a nice bell-shaped curve. We would consider this a normal distribution. Whenever we have a random variable that is based on the summation of other random variables, this new random variable will tend to have a distribution that is bell-shaped. There are many variables that can have a normal distribution. Some examples are on the slide. These will also include most characteristics from a manufacturing process. A continuous random variable x is said to have a normal distribution with parameters mu and sigma, with the PDF given on the slide. This PDF is quite complicated, so do not worry about memorizing it. It turns out that if x has a normal distribution, then the mean of x is mu and the variance is sigma square. Since the mean is a measure of center and the standard deviation is a measure of spread, we can use these things to tell us about the characteristics of the curve. We can see from the curves that changing the mean will shift where the center of the distribution lies. Also, as we increase the standard deviation, the curve becomes heavier tailed and fatter in the middle. Note here that for all 3 curves, the total area under the curve must remain 1. This is why, as variation increases, the peak must become smaller. We need to know how to find probabilities from a normal distribution. We would like to integrate the PDF to get the CDF. This is something that you cannot do in this case. We do have tables of probabilities available for a certain type of normal distribution. This is the normal distribution that has a mean 0 and variance 1. We call this the standard normal distribution. If a random variable z has a normal distribution with mean 0 and variance 1, we get a standard normal distribution. The PDF of z is in the slide. Notice that it is much simpler than the typical PDF for a normal distribution. We can now use this distribution to get the CDF. We will actually not need to do any integration since we have those tables that I spoke of on the previous slide. But the next question is, how do we use them? We will first find something called the z-score. We will do this utilizing the equation given in the slide. Next, we need to decide on how to use this value to find probabilities. We can use the standard normal tables to find the probabilities. Your textbook has this table in it. It is in Table A. For each value of z, there is a corresponding probability in the table based on the CDF. Based on what you see in the slide, we will manipulate these values to find probabilities for greater than and in between 2 values. Most statistical packages will also be able to give you the probabilities from a normal distribution. Let's do an example. We have a random variable that follows a normal distribution with mean 80 and standard deviation 10. The problem is asking for some probabilities, and the last part asks for a value for x. The solutions are on the next couple of slides. The procedure that we will follow to discover the probabilities is as follows. First, find the value for z, then determine the CDF value for the corresponding z from the standard normal tables. Finally, manipulate this value to find the probability. Go ahead and make sure that the answers you come up with match the answers on the slide. For the fourth part, we will do the same thing, except we need to find probabilities for both values and subtract them. As for the fifth part, we have a probability and we need to determine x. This is basically like working backwards. We will do this by determining the z value based on the probability, then use the equation for z to determine the value of x. Since we are using the standard normal distribution, there is another interesting property called the empirical rule. It states that if the distribution is standard normal, then the properties in the slide hold. Let's look at an example of this. A bottle fill process is running in statistical control. This means that the variation in the measurements from this process seem to be random. The fill level follows a normal distribution with mean 210 and standard deviation 3. Let's determine the range of values that represent each percentage. The solutions are on the next slide. In this case, we will just plug into the formula.
Now let's look at a more real-world example. Assume that we have a sample of size 50 cereal boxes off of a manufacturing line. The target weight of these boxes is 16 ounces. The weights will pass inspection if they are within 0.4 ounces from the target. Assume the weights come from a normal distribution. You can find the data in a file called serial box weights. The questions for this problem are on the next slide. Here are the questions that we wish to answer. You can find the solutions to this problem in a video called Normal Probabilities Serial Box Weight Answers.